what potential energy is. So potential energy means it's a way to store that energy. Now, in order to store the energy, I must have to be able to get the energy back. Meaning that if I give this ball some amount of kinetic energy, gravity takes it away, but then gravity gives it all back. That kinetic energy turns into a gravitational potential energy, and then it comes back into kinetic energy. That can give it back. On the other hand, if I take this box and I throw this box across the room, as it lands, I gave it a bunch of kinetic energy, gravity took some of it away, gave it all back, but now the box is stopped over there, okay? Meaning that friction had to stop it. Am I gonna get that energy back? No, because friction turned that energy into things like sound and heat. So if I go yell at that box and start it on fire, it's not gonna fly back through the air and get that kinetic energy. Okay? Chemical reactions are another great example. Whenever we have energy that turns into something like heat or sound, something along those lines, we no longer can get it back. The applied forces kind of fits that chemical energy. If I lift up this block, my body has expended energy. Now, me bringing the block back down, gravity's trying to give that energy back to me, but is it turning back into ATP in my arm? No, I've lost that energy, okay? So these are one directional, whereas gravity, elastic, electrostatic forces, these are conservative forces, we call it. So that energy can come back. It can go both ways. So if we're gonna have potential energy, we need a conservative force. So at this point, we're gonna read through the requirements for a conservative force. So one, it can be expressed as a difference between the initial and final values of a potential energy function. Okay, so a conservative force clearly can be talked about with a potential energy function. Okay, well, you can only have potential energy if you have a conservative force, so we'll go with that, that's okay. It is reversible, that is key. If we give the energy, it's gotta give the energy back. And then it is independent of the path of the body and depends only on the starting and ending point. So that's very similar to the first one. It just cares about where you start and end. No matter what we do, so like if I lift the block up here, but I set it down over here, gravity doesn't care that it's in a different location. If it's changing the same height, same final end height, we're good. And then when the starting and ending points are the same, the total work is 0. Okay, so we're going to use that last one. And this is what we call the box test. Okay. So if we want to see if a force is conservative or not, we're going to do something called the box test. How the box test works is you start on a coordinate system, and basically you start at your 0, 0 point, and you typically go up to a given point, maybe 1 meter up. And then you go over 1 meter, down 1 meter, and back 1 meter. And the idea is we've started and ended in the same spot. So our net work should be 0. So all we have to do is find the work of each one of these legs of our trip, and then add up all of those works and see if it equals 0. So we're going to test this theory. So if this is 0, we have ourselves a conservative force, meaning we can create a potential energy function from that force function. And that's what we're going to be doing later, but this is just our general test. So in recap here, potential energy is a stored form of energy, meaning if we give that energy, we can get that energy back. Only conservative forces can do this. Our examples we're going to use in this chapter, gravity and elastic forces, and we can then have other ones that are just kind of made up, but we're going to use them to learn from. And so to test it, we need to just throw it through the box test to see if it will add up to 0. So in our next example here, we're going to go ahead and try that box test out.